Well, hello again. Welcome to the next thermo video. We're going to call this video Finding H4, but that's a little misleading because it's only finding H4 if our Rankine cycle only has 4 components, where 1 is between the boiler and the turbine, 2 is between the turbine and the condenser, 3 between the condenser and the pump, and 4 is after the pump. So a better term for this video would be finding H after a pump. We find H1 off of the superheated vapor tables. We find the S at 1 and go to the pressure at 2, and we find 0.2 usually in the vapor dome in the table A2 or table A2 or A3, A2E or A3E. 0.3 we also find in the saturation tables 2 or 3, and it's the saturated liquid value. So for points 1, 2, and 3, we find them using the tables. 0.4 we do not. There's just a different process, and the purpose of this video is to show us that process. I'm going to run a first law analysis on the pump. I'll let the pump be the system. And I'm going to show that the work on the system is transfer of energy in from some external source, usually a motor. What comes into the system is 0.3, and what leaves the system is 0.4. This is in steady state, so I don't need to worry about any initial or final energy. All I need to worry about is what comes in, H3, what comes on, work on, any energy out, nope. Does anything leave? Yep, H4. So there's the first law analysis. So rearrange this, work on is equal to H4 minus H3. So where we're going is we're just going to rearrange this equation to solve for H4. H4 equals work on plus H3, or H3 plus work on. And that kind of makes some sense to us, doesn't it? Let me rewrite that one more time. H4 equals whatever the H was at 3. So whatever energy the steam brought in to the pump, plus whatever energy we bring in the terms of work, so whatever energy came into the pump, in the fluid, plus whatever energy the pump itself added, equals whatever energy is left. Pretty straightforward. Well, what it turns out is that we have another equation for work in terms of other properties. It turns out that the equation for work is, and this is an integral, it's the integral of pressure with respect to volume, integral of pressure with respect to volume. It comes from force times distance, but that is a derivation that we would do in advanced Rankine cycles. What we do when we do this integral and get all of our constants is we find out that this work is equal to V3, so V3 times P4 minus P3. So the work of the pump is the specific volume of the fluid times the change in pressure. So here we go. H4 equals V3 times P4 minus P3 plus H3. Let's do a quick example to find H4. So let's say that we have a pressure in our boiler of 2000 psi and a pressure in the condenser of 2 psi. And what I'd like you to do now is press pause and find H3 and V3. And I guess before you do that, just a quick reminder of where point 3 is. It's at the low pressure. As a saturated liquid. Okay, press pause, find H3 and V3. All right, well, welcome back. I hope you went to table A3E, which is the saturation table for pressure, and went to 2 psi and said this is a saturated liquid. So as a saturated liquid, I use VF. VF is 0.01623 feet cubed per pound mass, and HF (94.02 BTUs per pound mass. I better write those down. Give me just a second. I know you haven't written down, but that doesn't do me a lot of good. There we go. So H3 is 94.02 BTUs per pound mass, and V3 is 0.01623 feet cubed per pound mass. All right, now we'll just do a quick calculation. I've been doing this for many years, and I'll tell you what, I have great sympathy for freshmen who forget how to convert units, but for juniors and seniors, zero sympathy, nada, none. And I'll tell you what I think of juniors and seniors who don't. Yeah, here's what I think. Yeah, I think that's stupid. Don't forget to convert your units. Yeah, so there. Don't forget to convert your units. So the equation was H4 equals H3, so 94.02 BTUs per pound mass, plus V3, 0.01623 feet cubed per pound mass, times the difference in pressure. Well, 2,000 minus 2 is 1,998 pounds force per inch squared. You have no idea how many times my juniors and seniors, like you, have just done this math and added it to 94.02. Not acceptable. You cannot add a foot cube pound force over pound mass inch squared to a BTU. Illegal. So let's take a look using the famous railroad track method how to do this conversion. First thing we need to get rid of are those inches squared. So 12 inches is a foot. If I square the foot, and the 1 and the inch and the 12, I can get rid of my inches squared. And now look, we can cancel the feet squared with this feet cubed, and now we have foot-pounds per pound mass. Well, we need one more conversion factor. We need to convert foot-pounds to BTUs. Well, if you do this enough times, you'll remember, if not, you just look it up in the cover of the book, that there are 778 foot-pounds in a BTU. Foot-pounds in a BTU. So foot-pounds, foot and pounds, foot and pounds. And we are left with BTUs per pound mass. Let me press pause and do that math, and then we'll be done. So all of that math, the 0.01623 times the 1998 times the 144 divided by the 778, that was equal to 6. 94.02 plus 6, H4, is 100.02 BTUs per pound mass. That is how you find H4. We do not repeat the entropy process that we use to go from 1 to 2. That doesn't work down here. Instead, we use this process for finding the H after a pump. Have a nice day. Oh, and by the way, don't forget to convert your units.